Radar technology is one of the most important modern detection systems used for surveillance, navigation, defense, meteorology, aviation, disaster management, and space observation. It works by transmitting radio waves and receiving their reflected echoes from objects such as aircraft, ships, rain clouds, missiles, vehicles, or satellites. Radar can accurately determine distance, direction, speed, and movement of targets in all weather conditions, during both day and night, making it more reliable than optical systems. What is radar? The term radar stands for radio detection and ranging. It is an active electromagnetic sensing system that uses radio or microwave waves to detect, locate, track and identify objects at considerable distances. A transmitter emits radio pulses toward a target and the reflected energy returns as an echo to the receiver. By measuring the time delay, antenna direction, and Doppler frequency shift, the radar calculates range, position, and velocity. Modern radar systems operate from nearly 400 MHz to 40 GHz frequencies and are widely used in military operations, weather forecasting, transportation safety, remote sensing and satellite monitoring. Parts of radar. Radar systems consist of multiple integrated components that collectively perform transmission, reception, processing and target tracking functions. Transmitter. The transmitter generates high-power electromagnetic pulses in radio or microwave frequencies. Modern radars use magnetrons, klystrons, traveling wave tubes, or solid-state transmitters depending on power, bandwidth, and operational requirements. Antenna. The antenna radiates radio waves into space and receives reflected echoes from targets. Traditional radars use rotating parabolic antennas, while modern AESA systems electronically steer beams within microseconds without moving parts. Receiver. The receiver captures weak reflected signals and amplifies them for further processing. Radar receivers require high sensitivity because echo signals may be extremely weak compared to transmitted energy. Duplexer. Duplexer acts as a switching device allowing a single antenna to alternate between transmitting and receiving modes. It protects the sensitive receiver from high-power transmitted pulses. Signal processor. Signal processors separate desired target echoes from unwanted clutter such as rain, birds, land reflections, or interference. Modern systems use digital signal processing and Doppler filtering for precise target identification. Display unit. Radar displays present processed information on screens such as PPI displays. Targets appear as bright dots, while weather radars show rainfall intensity using color-coded representations. System control unit. This unit synchronizes transmitter timing, antenna rotation, pulse repetition frequency, receiver operation, and display functions to ensure integrated radar operation under varying environmental conditions. Power supply system. Radar requires reliable power systems because transmitters may operate from kilowatts to megawatts of power depending on applications such as air defense or missile tracking. Radar technology historical evolution. Radar technology evolved gradually from basic radio wave experiments to advanced electronically scanned systems used in defense, weather forecasting and space monitoring. Discovery. 1886 German physicist Heinrich Hertz demonstrated that radio waves could reflect from metallic objects, establishing the scientific basis for future radar technology and electromagnetic detection systems. Christian Hulsmeyer experiment. 1904 Christian Hulsmeyer demonstrated a ship detection device called telemobiloscope capable of identifying vessels in dense fog using reflected radio waves, becoming the earliest practical radar-like system. Robert Watson Watt development. 1935 British scientist Robert Watson Watt developed the first practical aircraft detection radar called Chain Home, capable of detecting aircraft nearly 64 kilometers away before World War II. World War II. 1939 to 1945 radar transformed warfare in WW2 by enabling Britain to detect incoming Luftwaffe aircraft during the Battle of Britain and allowing Allied naval forces to detect submarines and ships effectively. Magnetron innovation. 1940 The cavity magnetron developed in Britain enabled compact microwave radar systems with improved resolution, portability and operational efficiency for military and airborne applications. Doppler radar introduction, 1954 Doppler radar technology enabled measurement of target velocity using frequency shifts, revolutionizing meteorology, storm forecasting, missile tracking and moving target detection. India's early radar systems, 1970 to 1980 India installed its first S-band cyclone detection radar at Visakhapatnam in 1970 and commissioned its first locally manufactured radar in Mumbai during 1980. Modern digital radar era, contemporary radars use digital processing, phased array systems, machine learning and AESA technologies for simultaneous multi-target tracking, electronic warfare resistance and precision surveillance. Radar technology types. Radar systems are classified according to operating frequency bands and specialized applications across defense, weather monitoring, aviation, navigation, and remote sensing. Based on bands. P/UHF band radar, operating between 0.3 to 1 GHz, these radars provide very long-range surveillance, foliage penetration, stealth aircraft detection and over-the-horizon capabilities. India's LRDE low-band radar belongs to this category. L-band radar. L-band radars operate between 1 to 2 GHz and are used for long-range air surveillance and air traffic control. NASA ISRO/NISR uses L-band radar at 1.25 GHz. S-band radar. S-band systems operating between 2 to 4 GHz are widely used for cyclone tracking, weather monitoring and ship navigation because of superior rain penetration and long operational range. C-band radar. C-band radars function between 4 to 8 GHz and are extensively used in Doppler weather radar networks. IMD mainly uses C-band radars with nearly 250 km coverage range. X-band radar. X-band radars operate between 8 to 12 GHz and provide high-resolution imaging for missile guidance, fighter aircraft, rainfall monitoring, maritime surveillance, and airport surface detection systems. Ka-band radar. Ka-band radar systems provide extremely high-resolution short-range observations for automotive safety systems, speed guns, collision warning, and satellite imaging applications. Based on purpose. Weather radar. Weather radars monitor rainfall, thunderstorms, cyclones, wind movement, and severe weather systems. Doppler weather radars are critical for flood forecasting and disaster warning systems. Air surveillance radar. These radars detect and track aircraft, missiles, and hostile aerial targets. Air defense systems and airports rely heavily on surveillance radar for safety and security. Synthetic aperture radar. SAR systems mounted on satellites or aircraft generate high-resolution Earth images through cloud cover and darkness for agriculture, disaster monitoring, and terrain mapping. Over-the-horizon radar. OTH radars use HF waves reflected by the ionosphere to detect targets up to 3,000 kilometers beyond Earth's curvature for strategic early warning applications. Passive and bistatic radar. Passive radar systems use existing radio transmissions instead of dedicated transmitters, making them difficult to detect and useful against stealth aircraft and electronic warfare environments. Automotive radar. Automotive radar systems operating around 77 GHz support adaptive cruise control, collision avoidance, blind spot detection, autonomous vehicles, and emergency braking technologies. Modes of radar technology. Different radar modes are designed to measure distance, velocity, and target movement according to operational requirements and technological capabilities. Pulsed radar. Pulsed radar sends short bursts of radio energy and listens for echoes between pulses. It accurately measures target range and direction for air traffic control and weather monitoring. Continuous wave, CW, radar. CW radar continuously transmits radio waves without interruption. It measures target velocity through Doppler frequency shifts but cannot directly determine range due to absence of pulse timing. Pulsed Doppler radar. Pulsed Doppler radar combines pulse transmission with Doppler analysis, enabling simultaneous measurement of target range and velocity. It is widely used in fighter aircraft, defense, and weather systems. FMCW radar, frequency modulated continuous wave radar, continuously varies transmitted frequency and determines range through frequency differences between transmitted and reflected signals. It is common in automotive and drone detection systems. Radar technology in India. India has rapidly expanded radar infrastructure across meteorology, defense, aerospace, maritime security, and disaster management through indigenous development and international collaboration. IMD Doppler Weather Radar Network. India Meteorological Department operates extensive C-band and S-band Doppler weather radar networks for cyclone tracking, monsoon monitoring, flash flood forecasting, and severe weather warnings. Mission Mausam Initiative, approved in September 2024 with 2,000 Indian rupees crore allocation. Mission Mausam aims to modernize India's meteorological infrastructure through installation of 60 weather radars by 2026. Expansion of Doppler radar systems. India plans installation of 56 additional Doppler weather radars and 10 X-band systems for Northeast India and Himachal Pradesh's Lahaul-Spiti region. Vayunad X-band radar project. After devastating Kerala landslides in July 2024 causing over 200 deaths, India approved an X-band radar in Vayunad for hyperlocal rainfall and landslide monitoring. Mangaluru C-band radar. India approved a C-band radar in Mangaluru alongside the Vayunad radar project to provide broader regional weather coverage across Western Ghats and Arabian Sea regions. NISAR satellite mission. NASA ISRO synthetic aperture radar mission scheduled for 2025 will map Earth every 12 days using L-band and S-band SAR technologies with nearly 85 TB daily data generation. Uttam AESA radar, developed by DRDO and LRDE. Uttam AESA is an indigenous X-band fighter radar designed for LCA Tejas with simultaneous air-to-air and air-to-ground operational capability. Kshitij AESA radar, unveiled in 2024, Kshitij is an indigenous maritime X-band AESA radar developed for maritime patrol aircraft and surveillance across India's exclusive economic zone. Swordfish Long-Range Tracking Radar. Swordfish LRTR forms part of India's ballistic missile defense program and tracks incoming ballistic missiles over long distances using high-power radar systems. RISAT Satellite Series. RISAT satellites equipped with SAR technology provide all-weather Earth observation for agriculture monitoring, disaster assessment, defense surveillance and environmental management. Indigenous research institutions, organizations such as DRDO, LRDE, ISRO, IMD, and IITM Pune are leading India's radar research, indigenous manufacturing and meteorological modernization initiatives. Rainfall monitoring. India expanded rainfall monitoring stations beyond 7,000 by 2024, improving real-time monsoon forecasting, agricultural planning and disaster preparedness capabilities nationwide. Working process of radar technology. Radar operates through a systematic process involving transmission, reflection, reception, calculation, and display of electromagnetic signals from targets. Generation of radio waves. The transmitter produces high-frequency electromagnetic pulses at precisely controlled frequencies depending on radar type, operational purpose, and required detection range. Transmission through antenna. The antenna radiates these pulses outward as a narrow beam scanning a specific region where aircraft, ships, storms, or other targets are expected. Reflection from target. When radio waves strike an object such as aircraft, raindrops, ships, or missiles, part of the electromagnetic energy reflects back toward the radar system as echoes. Reception of echo signal. The receiver captures the reflected echoes using the same antenna or a separate receiving antenna and converts them into electrical signals for analysis. Range calculation. Radar calculates distance using the formula distance equals speed of light times time delay, divided by 2, because the radio pulse travels to the target and back. Direction determination. Target direction is determined from antenna orientation at the exact moment the reflected echo signal is received by the radar receiver. Doppler shift analysis. Moving targets alter reflected wave frequency through Doppler effect. Increasing frequency indicates approach, while decreasing frequency indicates movement away from radar. Signal processing and filtering. Digital processors remove clutter caused by land, rain, birds, or interference and identify genuine targets using Doppler filtering and advanced processing algorithms. Display and tracking. Final processed information appears on radar displays showing target range, position, speed, altitude, and movement path for operators or automated tracking systems. Radar technology uses. Radar technology has extensive applications in defense, aviation, disaster management, transportation, agriculture, environmental monitoring, and scientific research. Meteorology and weather forecasting. Doppler weather radars monitor cyclones, thunderstorms, rainfall intensity, monsoon movement, and flash floods. India uses radar-based early warning systems for disaster risk reduction. Air traffic control. Airports use primary and secondary surveillance radars to track aircraft positions, altitude, identity, and movement, ensuring safe aircraft navigation and collision prevention. Military and defense operations. Radar supports air defense, missile guidance, naval surveillance, ballistic missile detection, battlefield monitoring, fire control systems and electronic warfare operations. Maritime navigation. Ships use radar to detect coastlines, vessels, icebergs, and navigation hazards during fog, storms and darkness for safe maritime transportation and coastal security. Space surveillance. Radar tracks satellites, orbital debris, asteroids, and spacecraft for space situational awareness, planetary defense and monitoring of near-Earth objects. Agriculture and remote sensing. SAR satellites monitor crop growth, soil moisture, groundwater, floods, glacier movement, deforestation and land use changes throughout the year despite cloud cover. Traffic management and speed detection. Ka-band Doppler radar guns monitor vehicle speeds, while intelligent traffic systems detect congestion, collisions, and stranded vehicles on highways and urban roads. Automotive safety systems. Modern vehicles use radar for adaptive cruise control, collision avoidance, blind spot monitoring, emergency braking, parking assistance and autonomous driving support. Geological and engineering applications. Ground-penetrating radar detects underground pipes, tunnels, archaeological remains, buried cables and subsurface geological structures without excavation. Disaster management and landslide monitoring. INSAR and Doppler radar systems help identify landslide-prone regions, monitor ground deformation and improve flood and cyclone warning systems. Medical applications. Millimeter wave radar supports non-contact monitoring of breathing patterns, heart rate, elderly care, patient observation, and hospital safety systems. Environmental monitoring. Radar technology monitors sea waves, ocean winds, glaciers, forests, wetlands, volcanic activity, and climate-related changes for scientific and environmental management purposes. Law enforcement and security. Radar systems support border surveillance, drone detection, airport screening, intrusion monitoring and law enforcement activities related to traffic and security management. Scientific and planetary research. Radar astronomy studies planets, moons, asteroids and cosmic bodies, while satellite radar altimeters measure sea level rise and climate change indicators globally.